Let's see how we can relate the pressure of a gas to the motion of the molecules in your gas sample. Let's start with something simple. Let's say you just have one molecule with mass m traveling at constant speed v, a distance L along the x-axis. So let's say you have a container, and these are the walls of your container right here, okay? And your molecule is moving back and forth between these two walls right here. So here's a wall here, here's a wall here, and your molecule is moving at the speed v, going that way, okay? Here's your molecule. It collides with the wall over here, and it travels a distance L from one wall to the other, so the round trip distance is 2L. So if the speed is v, round trip distance is 2L, divided by the time it takes to make that round trip, then v is 2L over the time it takes to make the round trip. So the time between collisions with one wall would just be, let's just rearrange this, solve for t, that would be 2L divided by v, okay? Now, the change in velocity with every collision with one wall is negative v minus v. What does that mean? If it's moving with speed v initially, okay, then with velocity, then we take the velocity as positive in that direction. Then when it's moving back at the same speed, okay, same speed, but in opposite direction, the velocity will now be negative v, since we're taking the direction to the right here as a positive direction. So the final velocity is negative v minus the initial velocity, which is v. So the change in velocity, delta v, is equal to negative 2v. Divide that by the time, okay, it takes between collisions with that one particular wall. That time is 2L over v, and so that gives you your acceleration. So acceleration is change in velocity divided by time, okay, elapsed time. So let's simplify this. I have my 2 here cancels out. I have v, negative v over L over v, so I move my fraction up and flip it, so I have minus v times v over L. So that gives me negative v squared over L for my acceleration. Since the molecule is being accelerated, then there must be a force acting on that molecule, and the force on that molecule when it's accelerated is given by mass times acceleration, Newton's second law. So mass times the acceleration, which happens to be negative v squared over L. Okay? Since there's a force on the molecule, according to Newton's third law, the molecule also exerts on the wall, so there's an equal and opposite force acting on the wall. So it's positive mv squared over L, since the force on the molecule is negative mv squared over L. Okay, so the pressure on the wall due to that one molecule would be the force on the wall divided by the area of the wall. So if you imagine this is your area of the wall, okay, and the distance between the walls is L, you can see that if I have mv squared, okay, over L divided by the area, so I have mv squared over L divided by the area, I get mv squared over area times length. Area times length, that's just the volume of your container. Okay, so the area times length is just the volume of the container. And so you can rewrite this. You can say that's basically then equal to 2 times the kinetic energy divided by the volume. Why is that? Kinetic energy is defined to be 1/2 mv squared. Okay, so 2 times 1/2 mv squared divided by v. Your v2 cancels out, so you can see that's where your mv squared is. So basically, what are we saying? The pressure due to that one molecule is due to the kinetic energy of that molecule. It's related to the kinetic energy of that molecule. Okay, so collisions of molecules with a wall lead to what we perceive as the pressure on the wall. Okay. So what if you have n molecules, which is with our typical scenario, you'll have lots and lots and lots and lots of molecules in your container, and they're all moving in and there. In fact, they're going to be moving randomly, okay, in all possible directions. And so, if you did carry on this analysis that we did here and extend it to 3 dimensions with lots of molecules, you'll find that for n molecules, the pressure will be equal to 2/3 times the number of molecules n times the average kinetic energy of those molecules divided by the volume. Average kinetic energy means kinetic energy of molecule 1 plus kinetic energy of molecule 2 plus kinetic energy of molecule 3 and so on. All of that divided by the number of molecules. Okay? So n times kinetic energy, in a way, that's the total kinetic energy. So n times the average kinetic energy. So if you multiply this by n, so remember this is the average kinetic energy. So those brackets, the less than and greater than sign around the KE means average. Okay, so this means average. So multiply that by n, that gives you the total kinetic energy. Okay, so uh, the more molecule, what happens if you have more molecules then? The more molecules you have, then everything else being the same, then you have a higher pressure, right? That makes sense. More molecules colliding with the wall, that exerts a greater pressure on the wall. The more energetic your molecules are, that means the faster those molecules are moving, or the more massive those molecules are. Remember, kinetic energy is 1/2 mv squared. What happens to your pressure? The greater the kinetic energies of the molecules, and that means greater pressure, because they're going to collide with the wall at a much faster speed, so you'll have greater acceleration happening to those molecules. That means they'll be imparting a greater force on the wall.